we fixed it. It was there was a design partition that was hanging around from an old file that we deleted, and the clock. It was telling us there was a timing error because there was just a piece of the design that just wasn't there.
Oh.
So like it was just we found it and deleted it, and then then that compile didn't finish, and it just took forever. We think we were using too many like registers or multipliers.
Logic elements or whatever.
Yeah, just something, and we reduced it and it finished easily. So like it was definitely something using too much.
Okay. So so one thing you're going to run into with Lab 2 when you start building big systems is the compile times. Actually, using the fitter, this phase is going to take a long time. And there's a couple of things to do. One is, of course, make sure that you're not trying to allocate 105% of the logic elements, because the fitter will try, and it's stupid, and then ultimately fail. But it takes a long time to decide you can't fit. Another possibility is in the tools menu is a section called advisors. Which help you set up the very large number of compile parameters that are available in Quartus. There's a few thousand settable parameters. But if you go to Tools Advisors menu, you'll find that there is something called the Timing Advisor, which helps you speed up a design. There's also something called the Compile Time Advisor, which allows you to trade off fast and sloppy for slow and good. And you may find that for testing, going to fast and sloppy is better. So spend a little time playing with the advisors. Also, a few of my designs have a locked partition on them, which is probably what you ran into, was a locked partition left over from one of my designs, probably.
Yeah, it was left over from a previous iteration of ours.
Oh, it was your own problem.
But
okay,
yeah.
But I do have, there's a locked partition on a few of my examples, which encapsulates the QSYS and HPS and tries to minimize recompilation of that. But you may want to unlock all of it to allow better optimization of timing, or maybe quicker optimization of timing. So there's a partition manager that you're going to want to investigate and figure out how to handle partitions. If you have any piece of your hierarchy which does not change, any piece of the hierarchy, so you can break the design along a module instantiation, any piece of the design can be frozen, can be locked as a partition. And that may speed things up once you get the partitions right. I got a message over the weekend that MLab instantiation was not working, I think for Cowan. Who's not here. And somebody marked it as a resolved feature over the weekend. It wasn't me. Did you resolve that problem?
Yes, for my outgroup, we just use the template of the quarters. Just use the single quarter ring. Just
for MLabs, and that worked.
Right.
Okay, so there's a memory page down here on the main page. There's a memory page. The last example at the bottom, or almost the last example at the bottom, has a QSys SRAM, Verilog instantiated M10K block, and a Verilog instantiated MLab block. So if you scroll down through this mess, you will find an SRAM M10K state machine to read and write M10K blocks. You'll find an MLab state machine to read and write MLabs. And then towards the bottom of the file, you'll find an M10K module a definition. Simple 2-port, and an MLab module, which instantiates correctly. Yes?
No.
Oh, I thought you know that. And someplace here, I think it was in the, oh, I printed it, oh, look at that. So, if you go down through the partition merge RAM summary, this is the FITR output summary. The FITR output gives you all kinds of information, but in particular, my MLab 20_32 module was auto-generated and resulted in type MLab. And the M10K block, which I forced to be an M10K block, is indicated as an M10K block. So if you have any doubts about what the system actually built, you should be able to find it here on the FITR summary. So again, examples of how to use static RAM M10K, QSys static RAM M10K blocks, which are really the same, they're just instantiated differently. And MLab blocks are all here. MLab M10K blocks are all single access blocks. You get to do one operation per port on each clock cycle. There is no, for both M10K and MLab, there is no automatic, there is no global clear. If you code a global clear into your module, then the compiler will say, those blocks don't support global clear. This fool must want logic elements as memory, and turns it back into logic elements. If you do multiple accesses on a single clock cycle, it will convert it back to, the compiler will convert it back to logic elements. So, you know, it takes some care. Yes?
So what is the advantage of an M10K block and MLab block?
The advantage of M10K and MLab is it's much denser than logic element memory. I believe that you have about 140 kilobits of memory if you use logic elements. You have about 400 MLab blocks, each of which is 32 bits by 20 words. And you have about 400 blocks of M10K, each one of which is 9 kilobits. M10K, 10 kilobits. So the trade-off is denser memory, but it's serial. So whenever you use one M10K block, you would expect to access it with a serial state machine. Any questions about this, about memory?
So apart from the different sizes, what's the difference between M10K and MLab?
Not much. They have about the same limitations. MLab has a slightly different readback characteristic than M10K in terms of asynchronous reads, but they're basically the same, except MLab blocks are smaller and maybe better suited for small register sets like a CPU register set, where you don't want to use up a whole M10K block.
So for the system we were talking about last time during class, where we would allocate a separate memory block for every scan for every unit of parallelization for the Mandelbrot set, which of the two memory blocks would be more appropriate?
Depends on the size of your block. If you were going to put all of display memory into block memory, I would say M10K blocks, because I don't think there's enough MLab space. So if you wanted to tile your VGA display into N solvers, each one of which had a memory block then you would probably want to divide the screen into the appropriate size sections so that one or a few M10K blocks represented that section of the screen. And now you can do a separate access on every one of these blocks at every clock cycle, as long as they're instantiated separately. So you get a lot of memory bandwidth that way, not necessarily any more capacity, but more memory bandwidth. What else? So let's talk more about computing Mandelbrot set then. There's no more questions on lab 2. Yeah, in terms of drum, I suppose you could, if you have different regions of the drum, you could map each one. Let's say if you're going to have a 10 by 10 patch of drum, that's 100 nodes. There's 2 state variables per node, probably 3 state variables per node. You need about 1 M10K block to do that. One group noticed an interesting thing, which I hadn't thought about, but it was certainly true. And that is that you can set up a M10K block for 40 bits by 256. That means you can read back 40 bits at a time. That means you could read back in one cycle UN and UN minus 1, for instance. So you can get parallelism within a block because the length of the bitmap we're using for the numbers is less than half the size of the maximum width of the readback. So you could use a 10 by 10 would store UN and UN minus 1 for all 100 nodes, as long as your state machine stepped through each node sequentially and read out UN and UN minus 1 plus the surrounding values, again sequentially read, do the operation, store back the result. Trade-offs here are memory capacity, memory bandwidth, number of logic elements, number of multipliers. And of course, there's a time constraint. You have to get done with a sample within 20.8 microseconds. Yeah, I was going to email you. So any questions about lab 2 at this point? Everybody's got a drum running on the FPGA? You try putting the 24 by 24 on the FPGA? Or are you going right to the 40 by 40? 40 by 50? Okay. Anybody else?
I mean, personally, System Verilog would make me want to cry, but
Yeah, well, you know, Verilog is a very emotional language. It's, yeah, I find myself wanting to punch the screen sometimes. But, yeah. Count, did you mark that question as resolved?
I could do it.
No, did you?
I
Because someone did.
Oh, really? Probably not.
It wasn't me.
Okay.
All right. Is it resolved in your mind what was wrong?
So we decided to go another route. Yeah.
Which was what?
I'm not another one of our group members.
I said, so we're gonna do anything else? We don't know what, but it's gonna be something else.
Yeah.
Okay. All right, let's talk about Mandelbrot then. So last time I introduced this whole thing by saying you're going to be implementing the recursion relation or the iterative relationship plus C, where Zn plus 1, Zn, and C are all complex numbers. And I'm suggesting that you use 4.23 format. Fits nicely into one multiplier. Has enough bits so that you can expect to do about 13 zooms. So you figure if your initial 640 by 480 image is going to use about 10 bits of address, 10 bits of precision on X and Y. And so then we can zoom about 13 times before we run out of pixels. So then question is, how many multiplies how many real multiplies do we have to do? Oh yes, and we're going to terminate this after some n greater than some n, max n, often set to be 1,000, but that has to be a settable parameter on your implementation. And for testing, I strongly suggest that you implement this the first thing, not the last thing, because it's really nice to be able to test with an iteration of 10, and it finishes instantaneously, and you can see if it works. So we're going to terminate for any given pixel on the screen when the number of iterations gets bigger than 1,000, or when the magnitude of Z n plus 1 is greater than, magnitude squared is greater than 4. That implies that we're going to have to do 2 multiplies here to get the magnitude, and 1 complex multiply is 3 multiplies. Oh, how do I know that? Well, let's just write it out. Let's say we have Z real plus j times z imaginary. So the z real and zi are both real numbers, right? Times z r plus j zi plus cr plus jci. And if we factor this all out and rearrange it, we find that what we need to calculate is z real times z real plus c real minus zi times zi, that being the real part, and the imaginary part, j times 2 zrci plus ci. So it multiplies 1, 2, 3, and then 2 more, 4, 5 down here. So it needs 5 multiplies. We need to do 5 multiplies per iteration. Josh.
Should that second part of the first term be zr plus jzi, not zjzi?
The zr times
up top.
zr
Up top,
plus
second
CR.
parentheses, a little to the right. Yeah, right there.
So we need 5 multipliers per iteration. So at one extreme, you could use 5 multipliers and do it all in about 2 cycles. Or you could use 1 multiplier and do it in 5 cycles.
Is there an easier way of finding squares rather than multiplying?
Is there an easier way of finding squares than multiplying? Such as?
The square root, there is a trick to find out. So there should be something that's square.
Oh, yes. No, there's no faster way to do that. So, yeah, what you're referring to are these weird approximations. Yeah, so there's this weird one. If you have a squared plus b squared to the 1/2, then within 4%, that's equal to the max of a comma b plus 0.4 times the min of a and b. I couldn't make that up. You try it, it works.
I was just asking about just a square term, like a square, is there an easier way to find out rather than multiplying it into the...
No. Not that I know of. So, 5 multiplies. Takes 2 cycles, you have to do these, then this. Or use 1 multiplier with a 5-state state machine. Yes.
So why doesn't computing z event plus 1 squared also take 3 multiplies? Because it took 3 multiplies to compute z event plus 1 by squaring zn.
This is equal to z real squared plus zi squared. Right? That's the magnitude of the complex numbers, 2 multiplies. So, but wait. On step n, we're multiplying the new z real. This is by the way the n plus first step, right? The z real is the I. That's 2 of the multipliers in the next step. So all we really need is 3 multipliers. So let's just write this all out, I guess. let's write out the canonical form first. You can imagine feeding in a ZR into a multiply module, which you instantiate, feed it in twice, bring it out, another multiply module, feed in ZI twice into that, bring this out, add them together, along with a third multiply, which takes one input from each. Oh, we also need CR, which gets fed into here. And this gets fed in with a minus sign. We're going to shift this to the right, to the left by 1, to multiply by 2 here. Add this to CI. So what's going to come out here then is Z real n plus 1. What comes out here will be ZI n plus 1. And of course we have to take n and add 1 to it and put out n plus 1. Because we have to keep track of the actual count. Then we're going to take ZR n plus 1 that we've just calculated up here, feed it twice into a multiplier. Add it to ZI n plus 1. Another multiplier into the adder. And ask, is this greater than 4? Is it greater than 4? Yes. Plot it. No. Is n greater than 1,000? Yes. Plot it. No. Repeat. Now, because of the limitations of the number system we're using, where we only have a range of plus minus 7, in principle, either the Z real or the ZI squared operation could overflow that calculation before you sum. Therefore, it is a good idea to find out if either of these is greater than 4, because if it is, the sum can't possibly be less than 4. And so you may have to do this check for greater than on both of these points also. If any of these is greater than 4, you terminate the calculation. So that's the 5 multiplier version of it.
What is the word at the end of the no branch coming out of n greater than 1,000?
Repeat.
So any number greater than 4 won't fit in your number system at all?
No, any number greater than 7 won't fit in my number
okay.
system. But any number greater than 4 is guaranteed divergence.
Mm-hmm.
So, how do we optimize this? Well, first of all, notice that this is the end for ZR n plus 1 and ZI n plus 1. These are two of the multipliers that will be used on the next time step. So we don't have to do this, and then do that same multiplication again up here. We just have to save these two results for the next time step. So how do you initialize it? What do you choose for the 0th time step? What's the value of ZR V squared n real I plus 1 ZI squared for the 0th time step?
It's 0.
It's 0, because last time I mentioned that you always start Z iteration, Z of 0 equals 0. So then we know what these two values are for the first time step we have to iterate up here. They're going to start out as identically 0. So there is no ambiguity about how to start the calculation, and no ambiguity about how to go step by step with 3 multipliers. Okay, 3 multipliers. We have 87 multipliers. (87 divided by 3) sounds like, well, 90 divided by 3 would be 30, so this must be 29. 29 pipelines you can build on the chip if you don't run out of something else first. 29 pipelines. If you run them all at 100 megahertz, and you do a 1-cycle calculation for this, that sounds like, or you pipeline it, so that sounds like 29 times 100 million. So that's about 2.9 gigaflops. That's pretty good.
Just trying to do the math. How many scan lines per pipeline would that be then?
Oh, well, if you broke it up by horizontal blocks, there's 480 active scan lines on the screen vertically. So that looks like about, I can't quite do that one in my head. You got a laptop, open, do the arithmetic.
Not sure.
That's the way I keep people honest. What's the answer?
It's 16 point something.
16, so 16 solvers. The rule is, if you have a laptop open and I ask you a question, you answer the question. All right? That's how I keep people honest with their laptops. I don't do it too often. Do it more in 4760 when people ask a lot of questions about data sheets. So, that says you can do, it'd be about 16 lines. It would be about 16 or 17 lines per solver, yeah. Is that big enough to get a good statistical sample? Maybe. What if you made the blocks non-sequential? What if you did, each solver did 1 line out of this block, and 1 line out of this block, and 1 line out of this block, and then the next solver did these lines so that every solver samples the entire screen at low density. That seems like it's guaranteed to be pretty good at sampling the, since you don't know what the geometry is, a uniform sparse sampling has got to be about the best you can do. So if you serialize this, you could build a pipeline that I know you can do it in 5 cycles. You may be able to do it in 4 cycles. Build a pipeline that will produce a iteration on every cycle by using a serial, by using a 1 multiplier. Pipelining the solver, you can produce an output per cycle. Can't do better than that. And you have a certain amount of overhead because some pixels will only take an iteration to diverge, and by the time you load up the pipeline, it's going to be done. So you'll have some waste at low repetitions, where you're in a region of the Mandelbrot set that has low repetition. So out here, you're going to waste a lot of time because there's only 1 iteration necessary to diverge. Here, you'll save a lot of time because there's 1,000 iterations necessary. Although most people are probably going to describe a rectangle and not bother to compute anything inside the rectangle. Another rectangle in here. Rectangles are easier bound than circles. That's why you use a rectangle.
For the optimization I saw mentioned, what we're defined is that if in 2 cycles n then plus 1 is z has the same value, then it's obviously reached a fixed point isn't going to change at all.
That's also true. If there's no change in the output between 2 cycles, then it's a fixed point and it is guaranteed to stay inside, and so you can just stop iterating. That costs some extra logic, and whether it's worth it or not, I don't know the numbers on that. That would be interesting to simulate and see which way it comes out. I just don't know. So there's an implication here. If you were to hard code these scan lines on which you calculate for each solver, let's say solver 1 takes this line, this line, this line, this line, this line, and that line, then you don't have to do a very big calculation to dispatch pixels to a given solver. In fact, all you need to do to pass off to the solver is some C-real, some CI, which is the real and the imaginary part of the point you're solving. Then the delta CR and the delta CI, how much C changes from pixel to pixel, which is going to be determined by the absolute range divided by the number of pixels. You go +1 to -1 vertically in 480 steps, you can get the delta easily. You zoom in a factor of 2, you're going to have the delta. So zooming is easy. Calculating the next point which you have to calculate is easy. You add delta CR to CR, you get the next point to calculate. So dispatching points is as easy as preloading the solvers, each solver with 4 numbers. which in this situation you could do from the HPX if you wanted. Or from a RAM or ROM. Somebody was using this strange construction dollar read file, something like that. Or using, what was it called? Dollar read mem. So what, I looked it up, what Quartus does with dollar read mem is it generates a memory image file for you and makes a ROM. So that's one way of making a ROM easily, without having to figure out how to make a memory image file. What do you think? Oh, you know, we have to talk about final projects. That's only 3 weeks away. And so sometime about a week and a half from now, so let's say the middle of Lab 3, the middle week of Lab 3, I need you to be ready to stand up in front of the class and give a 5-minute pitch on what you're going to build. Okay? This is required. So if people don't show up for that lecture, they get a 0 on that. Yes, what?
So the beginning of Lab 3 is in next week?
Yes.
Like next Monday or
Yeah.
Wednesday?
No, this Friday, Lab 3 starts.
This Friday. All right. I was just,
It ends on, Lab 2 ends on Friday, so Lab 3 starts on Friday.
okay, fair. I was just checking the lecture. I didn't know if that.
So, oh, you're saying, will there be a lecture on Friday?
Yeah,
What
because
you
we
say?
usually do it in the, I didn't know.
No, I'll do it in lecture. We'll stand up. You'll do a 5-minute stand up to pitch your proposal to the
All right.
class. So it's not too early to start thinking about what you're going to build. If you need a piece of hardware, you got to tell me before the final project starts if we expect to get it on time. If you need a camera, you tell me. This particular architecture has native support for television input, NTSC. NTSC is the old, obsolete analog standard in the US. Except it's not obsolete. People still use it for all kinds of closed circuit stuff. So there's native support in the hardware for NTSC cameras. You can also interface digital cameras like the OV6067 or 6760, whatever it is. If you need something else, you need to tell me, like soon. Josh.
Do we have a budget?
No budget. You can spend whatever you want. I'm spending nothing. Unless I can reuse it. I'll buy cameras that I can reuse. Actually, that's slightly misleading because this is the last time I'm teaching this course. So, I won't be reusing it, but somebody else might. But, so, stuff that's generally useful for the lab, I'll consider buying out of lab budget. But if it's something fairly specific, like last year, one group bought 4 digital cameras, small digital cameras, so they could interface all 4 cameras to the FPGA. And then take images of an object from 4 different directions, project them into a pyramid, and get kind of a 3D display inside of a small pyramid being reflected off of a VGA screen. So, in that case, they bought the cameras and the small pyramid and all the mirrors and stuff. Any thoughts on final projects? Anybody had any initial thoughts on final projects? DSP is always in good taste. So, sonification, 3D mapping of the audio world to your ears using your head-related transfer function is good fun. It's probably of general use for virtual reality. Music synthesis is fun. You have enough bandwidth here to do a pretty good piano, if only you can figure out how. Including stiff strings modeled at the level of the partial differential equation for stiff bars. Some computer vision is possible. I've seen OpenCV running on these chips, but not with the version of Linux we have. Students had to bring up another version of Linux. Almost any reasonable game I'll go for. Reasonable compute-intensive game. Tetris, nah, not so much. You know, but if you want to make gesture-driven Tetris, sure, yeah. High-speed motor control, high-speed servo loops, where you need 1 million updates a second. Any thoughts? Did I see a hint? Tentative hand? No thoughts, no thoughts. It's been a long 2 weeks, folks.
So, on that day we'll be all pitch our projects to a class. If someone else's project sounds really fantastic, can we say, actually, the thing I pitched is less interesting than the thing you pitched. Can I work on your project?
I'm going to join your group. So I would be disinclined to do that. On the other hand, if 2 people pitch the same project, I'm fine with that. As always with these projects, it's easier to work on something if it's something you care about. So it's useful to try and relate a project you do in any course to some outside interest you have. Bicycling, drones, oh God, no drone testing. Whatever your interests are outside of class. I suppose if you wanted to automate, well, we had one group one year who automated Cricket 2007. Made a superhuman cricket player, cricket batter, using closed loop control from the video to hit the ball, and couldn't be beat. The students to do that had to build custom hardware to digitize the VGA channel at a video rate. Build a daughter board that plugged into the expansion connector of the FPGA. Took the output from that, deduced the region where the ball was appearing, calculated the velocity of the ball from the color of the ball, and made a closed loop PID controller, optimized PID controller. 3 guys, didn't sleep for 5 weeks. I don't recommend that. But they gotta run it. So games are always good. Games are hard. Saw a game once, it was sort of some sort of spitting meatballs onto skewers, some weird game. And highly animated, beautifully done, not one single line of sequential code in it. Every image was stored in hardware as memory image files. All bit blitting and compositing was done in hardware. It was, the mouse was being run from hardware. Completely seamless. By the way, we do have PS2 mice. If you want to run them from hardware, they're much easier than USB. We also have USB mice that you can run from the HPS. Start thinking. Any last minute questions?
Do you have a other library?